Welcome to the SEI podcast series, a production of the Carnegie Mellon University Software Engineering Institute. The SEI is a federally funded research and development center sponsored by the U.S. Department of Defense. A transcript of today's podcast is posted on the SEI website at sei.cmu.edu/podcasts.
Welcome to the SEI podcast series. My name is Suzanne Miller, and I'm a principal researcher in the SEI Software Solutions Division. Today, I'm joined by David Svoboda and Garret Wassermann, colleagues of mine that are both software engineers in the SEI CERT division. We're here to talk about their recent work with a programming language called Rust. And you may have seen our earlier podcast with David and Joseph Seibel discussing security issues in Rust. In this podcast, we're going to examine tools for understanding vulnerabilities in the Rust ecosystem, as well as the maturity of Rust overall, so that people can make better decisions about whether or not and how they want to use it. So I want to welcome both David and Garret. Thank you for joining us.
Thanks for having us.
Yeah, hi. Thank you.
So before we dive into our main topic, we always begin by having you tell us a little bit about yourselves, what brought each of you to the SEI, and what is special and wonderful about the work that you do here. So Garret, let's have you start.
Sure. I came to SEI originally in 2014 as a vulnerability analyst, where I was interested in learning more about cybersecurity and how to, defend all of our software, computers, and networks from various security threats that exist out there on the internet. And so for a number of years, I actually worked in the CERT Coordination Center, where I published vulnerability notes, which are publications that detail software security issues that exist in software that you use every day, as well as details of workarounds and fixes, patches, whatever is necessary to try to address the issue and improve the security. And we would work with both security researchers as well as the software vendors themselves to try to get these patches and information out to the public and improve our general security posture. And so as I was studying those vulnerabilities and learning more about software, I moved into more of executable code or binary code analysis work, where we try to take all the information that we've learned about how these vulnerabilities come about, basically, and turn it into tools that we can automate or at least assist with analysts in order to better understand vulnerabilities, to find them and to correct them. And so, I would say that the best part of the job has been to explore new ideas related to this. And that's what eventually brought me to looking into Rust for this blog post.
All right. And David, refresh everybody's memory as to sort of how you came here and what it is that you enjoy about working here.
Sure. I joined the SCI in 2007 in the Secure Coding Group. The Secure Coding Initiative was actually an offshoot of the Coordination Center, Garret's same Coordination Center. But we were focused on, the programming mistakes that allow these vulnerabilities to exist. And I had been a professional programmer for over 15 years before joining, but I discovered that secure coding was sort of the secret section of programming that programmers never worry about. Every programmer, if you want to be a programmer, you have to be an optimist. You have to assume that the input will be correct and all the data will work and nothing goes wrong, and then your program runs correctly and everything is beautiful and the angels sing. But life never turns out that way, and things go wrong. And I discovered that secure coding is really, I had an epiphany that, most people, when it comes to software security, most people are sinners. They create lots of vulnerabilities, problems, and, Garret's kept busy by detecting these things long after the software has been released. And I've taught secure coding, in lots of places over the world, and a lot of people have the same reaction. It is something of an epiphany to people, and they leave my course, and I say, go and sin no more. And they may still make mistakes, but they are all missionaries in this. It's almost a new religion of coding securely. So, that's also the really great thing about this job. It teaches people who think they know everything, and I was one of such person, that they are annoying for those of us who really do know everything.
Well, and we all have things to learn. And truly, the technology evolves in ways that we can't always predict what the vulnerabilities are going to be that come out of this new thing that we can do that we couldn't do before. So we all have to have a learning mindset if we want to not get taken by some of the new things that
Yes, technology has evolved to require a lot more security. You can thank the internet for that.
Yeah. Yes. Thank you, Internet. All right. So let's talk about Rust. And we've described Rust before, and I like the way you described it in our previous podcast. Is it's the first language that has really been able to compete with C in the embedded systems world for software, and it corrects some of the danger zones. I love that term. Some of the danger zones that are present in the C language. So that's one of the reasons that it's being adopted by people. So I don't know if there's anything else you want to say about the language before we get into your blog post and the vulnerabilities. So I'll let you answer that, David, if you have anything else you want to add.
I'll go ahead and add that these danger zones, everyone has been aware of the danger zones pretty much since the late 80s. The catch is, of course, that many languages like, so C++, for instance, tries to mitigate the danger zones by providing safer versions of many of the dangerous techniques that C has. So C++ will have vectors for doing safe array managing. They'll have variadic templates for handling variadic functions. But you can still use all the dangerous C mechanisms. Java tries to replace the runtime environment with a safe runtime environment that simply says, "Hey, you're trying to access, the 12th element of an array of only 10 elements.
Don't do that."
Yeah, your program is shut down now. So the problem, of course, is that Java imposes a performance constraint because it has to check that the array is only 10 elements long. And other languages like Python generally follow the same footsteps. They provide you a lot of safety, but they cost you in terms of performance, and they use more memory than C does. So Rust is the first language that tries to give you both the runtime performance and slim memory footprint of C while giving you the same safety that you get in Java and Python. They do this by adding lots of compiler checks, and that's why Rust should be able to compete with C in the embedded world and the small world where memory is limited and performance is truly critical.
Yes. And so that's really the exciting piece one of the exciting pieces of Rust. But there's also some exciting pieces about it has some constructs that we've talked about that actually correct some of the most egregious danger zones. But that is all happening within an ecosystem. Anytime we have a new language coming into the foreground, there's a lot that needs to go on with it, community building and all kinds of things. So we talk about that as the maturity of the language, right? So why is that maturity important in a programming language? And what do you think? Where do you think Rust fits in terms of the level of maturity and its ability to be supported, so that people that want to use it don't feel like they're kind of off on the edge?
So I wrote we kind of divided up the blog post where Garret provided the vulnerability detection in Rust, and I provided details on the maturity. And I realized when I started to write the maturity section that while I had an idea of what stability is, I didn't really know how to define maturity for languages. People say C is a mature language. Is it? I mean, why? So, I want creating a table saying, here's a whole bunch of properties that languages have that are considered to be mature. For instance, C has a standards body. It's a long name, ISO/IEC/JTC/SC22/WG14. The WG stands for working group, which is not very helpful, but the point is it is a committee of about 25 people or companies that steward the language. I've been on and off the committee for about, pretty much since I joined CERT. And so that's a sign that C is mature. It's not going to change. The committee itself is very conservative in that, they have a successful language. They don't want to change it. They want to make the changes that they make to it. They want to be as harmless as possible because there's lots and lots of C code out there, and they don't want to break it. So after I made the table, and the table is in the blog post, it took me a day to add that and get all the facts right. But that table kind of became the framework for the maturity section. And what I realized only after I made the table was that I still don't have a good definition of maturity, but the properties of maturity have changed for languages. In the 70s and 80s, when C was big, maturity was seen as having a bureaucracy, a committee to steward the language, and today, Rust, as well as languages like Python, don't have that. They just have a foundation, usually a not-for-profit company that stewards a language, but they are basically a bunch of volunteers, although they're usually volunteers from companies that say, you can spend some time, making Python better.
Right. So it's not quite an open source model, but it's moving more towards an open source model.
It's more towards open source, and it's more technical because Rust, for example, has Crater, which is, you can think of it as a continuous regression testing system that tests all of the Rust code out there.
Okay.
I mean, testing all the code out there was something completely unthinkable in the 70s and 80s. We only barely had the internet, and now not only is it thinkable, but it's actually being done. If you write some Rust code and you post it to GitHub and you add a test suite to it, then that test suite will be run by Crater, and if it fails, then you're going to get some sort of notification, and that is a sign of maturity for Rust. That is, well, it's very new, so I'm not sure if that's mature or not, but that's the way that Rust is measuring maturity. The definition of maturity is kind of immature itself.
Well, and that's fair. And the importance of that, though, is what you talked about before. You don't want to invest in a language like Rust, write a bunch of code, and embed it in hardware, and then have it change every 3 months just because somebody decided that this is better than that, and now my code doesn't run anymore, won't compile anymore because this piece of this construct's been taken away.
Precisely.
There's a level of you mentioned stability, right? There's an aspect of maturity that relates to the stability of the language. Is it still in a state where it's not very stable and it's changing all the time because people are still learning what works and doesn't work for the language, or has it matured enough that I feel safe that if I write something in Rust, it's not all of a sudden going to break in 3 months because the language has changed yet again, right? So, I mean, even though you may not have a strong academic definition of maturity, the concept of maturity, I think, is one that people can get in relationship to a language. So what I'm hearing you say is that Rust may not be as mature as a C language, but it is mature enough that people can consider using it for real world projects, not just for model problems, right? I see Garret enthusiastically nodding his head to that. Did you want to comment on that, Garret?
Yes, actually, to kind of expand from what David was talking about with maturity and what you're saying about feeling comfortable at writing new code in this, that's essentially what got us into looking at this, or certainly myself was the catalyst for looking at Rust, because the language and the ecosystem as a whole has matured so much. The language itself has matured, the compiler has matured. There's now a whole crates.io website where you can find libraries and that are fairly well developed and maturing to support many different types of programming. And because of this level of maturity, you're seeing businesses become much more interested in using it for their own applications, and also open source projects using it for their applications. And this has grown into, for example, the Linux kernel itself, which is such an important piece of software for the entire global internet. It's at the heart of so many devices and technologies and all. The kernel itself now has creating a project to support Rust code, which is very important because the Linux kernel standards were always focused on C.
Right.
In fact, C++ and other languages were always kind of frowned upon for various reasons. And so integrating a new systems level language like Rust is a really big deal into the Linux kernel, which is going to expand its exposure in the world. So, this moment of maturity where it's becoming part of such mission critical software is really the drive, the kind of alarm system. Alarm is maybe not the right word, but reminding us that this has really become such a mature thing that we need to start looking at it very seriously, like we would for C or C++ or any other type of software code.
Right. The fact that, so at about 20 years ago, Linus considered allowing C++ code to be added into the kernel, and he rejected it, mainly because C++ did not have a stable ABI, which is application binary interface. And so the fact that Linus is now, as of version 6.1, is now allowing kernel code to be written in Rust, that is it's a positive sign of maturity.
Right. No, that and that's a significant sign that this is not going away.
Right.
And so it's not going away, which means, Garret, that we really need to understand what are the vulnerabilities in Rust. It may address some of the vulnerabilities in C, but what are Rust's innate vulnerabilities that programmers need to be aware of and to be cautious of?
Yes. So Rust, as has been discussed, one of its primary features is to try to improve memory security by having a certain memory security model that it enforces through the compiler, and features of it, for example, called the borrow checker. One of the most important aspects of Rust is the concept of ownership of memory and borrowing access to it in different pieces of your software. And so that model provides a lot more protection from sort of common things, particularly towards C, where there is no borrow check or anything, right? You have to be very careful what you're doing. Rust is very opinionated. It's very trying to push you into more secure coding kind of by default. But that model, has certain limitations and doesn't necessarily cover all aspects. And so, we can look for types of vulnerabilities that exist out there. And one way that the global internet community looks at vulnerabilities is we catalog them in the CVE system. For folks that are familiar with CVE, it's a globally unique identifier for vulnerabilities that exist in software, where it can pinpoint, the type of vulnerability it is, what software it's in, what version of the software it's in, and what the fixes are, ideally. And that flows into a bunch of both public and private sector processes to make sure that our computers and networks are safe. And so when we look in the CVE catalog for Rust-related vulnerabilities, there's actually already several hundred of them that are already cataloged and exist and have been looked at and researched and
I want to stop you there just for a minute, because there's a way in which, if I heard you saying that and I don't understand the CVE system, I might go, oh my God, there's hundreds of vulnerabilities already. But compare that hundreds to how many are there for C?
Yes, good point. Yes, that is a part of the post.
Hundreds of thousands, I think. Have we reached 100,000 yet? CVEs, Garret?
Yeah, I'm not sure.
So in the larger scheme of things, the number of vulnerabilities are growing, and it's new, so that's going to grow as well. But it's not that you shouldn't be alarmed as a potential user because there are several hundred vulnerabilities already logged. Is that a statement?
Yes. So there are examples of vulnerabilities in software that uses Rust that have been cataloged in the CVE system, and we've identified a couple hundred of them in various software. And considering how much software exists in the world, literally tens of thousands of CVEs are assigned every year. So it's not necessarily a large amount of the vulnerabilities that exist out there, but it is a sign that Rust memory model is not perfect, that there are possibilities where vulnerabilities can creep in, even though it does a very good job at trying to prevent certain types of memory issues. they can creep in. You can end up with certain kinds of vulnerabilities related to memory, with like double freeze and things like that was, I think, one example we looked at in our blog post. So there are examples of vulnerabilities out there. And these vulnerabilities are not necessarily even in software that's in wide use. I think many of them were in lesser known libraries, for example. So all of this has to be taken into account, and that's part of the whole CVE security ecosystem, right? Looking at how severe are vulnerabilities, who might be impacted, how widespread is the impact, all that stuff. There's a lot that goes into it. But from a sort of a development and analysis perspective, it tells us that more work needs to be done in order to better understand the consequences of the Rust memory model and how its borrow checker works, and if there's problems with the borrow checker that we can improve in the future. And either way, improve our binary analysis tools so that we can better understand these vulnerabilities and find them after software has come out, so that we can, of course, engage in all of the appropriate processes to fix them and get fixes out to the public.
So are you perceiving that there's an active community that is actually trying to build some of the kinds of tools that you're talking about yet? Or is that something that is sort of we're not as mature with Rust in terms of having a lot of tool sets that try and help us do that analysis?
Yes, so there is a pretty mature community and many researchers that are looking at the binary analysis and code analysis aspects. But I think up until this point, a lot of that focus has been on the most common softwares that exist, which would be code that's written in C or C++, especially for like Intel x86 architectures. And so now that there's more devices, cell phones using ARM processors and all, there's more architectures to think about, and now there's more languages to think about.
Sure.
And of course, those languages get interpreted to the architectures. So we have kind of this expanding view of code analysis that goes beyond kind of its original research aspects, which is what makes all of this very interesting. How much of those assumptions in our analysis were actually assumptions that were based on the way that the C or C++ standard works, especially with how compilers translate it to, for example, the Intel architecture. Maybe not all of those assumptions were actually valid for general binary code. And those are the questions that our blog post starts to look at. And I think when you look at the Rust language standards that are being built up, they've made some very conscious decisions in the Rust language to actually break compatibility with C in certain aspects. For example, the name mangling that compilers do. At first, they actually investigated looking at making it compatible with the C standards, and then they kind of decided over time that just wasn't really long-term viable because of all the new features that are in the language, the modern features that provide security, right? So, there's breaks in the way that various programming language concepts are represented in the binary code from the ways Rust does it compared to the way C did it, and all of the C-related languages, the C-inspired languages that are around that whole ecosystem that tried very hard to keep compatibility.
I see. Okay. David, you had something you wanted to add?
Yeah, I would like to add something to Garrett's explanation of the number of CVEs we have in Rust, and that is that partially this was an explicit decision made by the Rust community, where as we said, Rust has a borrow checker which helps to enforce the memory safety, and they simply decided that any bug they had in the borrow checker merited its own CVE. This was kind of their way of taking security seriously, trying to generate faith and and make the language mature.
Right.
But that means that that should help to make sure that the borrow checker is bug free itself. But because bugs become CVEs and become public, shall we say, public embarrassments.
Well, and I take your point that they are not trying to sweep them under the rug, and that's the point. That's the thing that engenders trust, and that's when you have a language that advertises itself as being a language that is security centric,
Mm-hmm.
you have to take you have to take those seriously, or else you will lose trust very quickly.
In the short term, you can say it engenders mistrust because, hey, all these CVEs, but in the long term, it does engender trust
Right.
because, we're at least being open and honest about the stability and maturity of the language.
So I see a few potential areas of research coming out of what you guys are talking about. The SEI actually getting engaged in building analysis tools, the SEI evaluating analysis tools and the kind of ecosystem that they support. Also, helping the Rust language, as you said, researching the memory model that is being used, memory safety model that's used. What are you looking at as sort of future research in relationship to Rust?
I was going to simply suggest that we started scratching the surface of static analysis, both of Rust source code and of binary code, because as Garret noted earlier, Rust binaries, while they support more memory safety than C does, they often change things. For instance, they don't use the same name demangling that C does. They compact their structures, their data structures, differently than C, and that can confuse current binary analysis tools like Ghidra. We've been using Ghidra, which is mainly for binary analysis. It was released as open source by the NSA in 2019. It's a popular software for research. And Ghidra has a harder time with Rust binaries than with C binaries. That's something that can be easily fixed. It's just a bit of engineering work that needs to be done.
What about for you, Garret? What do you see as some of the research opportunities here?
Yes, I agree with what David was talking about there, that there's ecosystems of tools that exist that look at binary code and executable code analysis that we mentioned earlier. But because of the changes in the way the Rust language works and the way that it is represented in binary code, many of those tools need to be improved. And sometimes those improvements could probably be relatively easy, just engineering sort of decisions, just kind of throw people at it. But sometimes there might be more sophistication behind it. And, one example that comes to mind is right here at SEI, our CERT coordination team has the Pharos binary analysis framework, for example, which is a number of tools to help reverse engineering and help analysts do reverse engineering. And a lot of those tools, one example is a tool known as OO Analyzer, and it's called that because the OO is object-oriented. It's designed to recover object-oriented sort of code, but from this C++ perspective, from understanding how C++ classes and types and all are generally represented in binary code. And as we were mentioning, those assumptions are not necessarily true anymore, and they would need to be updated for Rust. And Rust type system is much more sophisticated than what you see in C++. So, there's some theoretical challenges there too, not even just engineering challenges, where we need to better understand kind of like the typing system as a whole and ask questions about how much of that type system can be recovered, because the compilation process itself loses a lot of that information from the source code when it moves to binary code. So, I think there's a lot of interesting challenges in reconstructing that and kind of decompiling. The Ghidra tool, for example, that David also mentioned, is a really great tool, and it has built-in disassembly and decompiler and all. But again, the decompiler is focused on C code.
Right.
So making it an accurate decompiler for Rust, I'm not entirely sure what all will go into that, but those are the interesting research projects, right? And we have our own extension for Ghidra that's known as Kaiju, that is meant to start kind of building up more binary analysis tools similar to Pharos, but whereas that's built on the Rose compiler framework, this would use Ghidra. And again, making those tools work properly with Rust code is all interesting open research questions that I'm interested in getting into.
Which takes us back to the maturity question, because you're not going to invest in that kind of research for tools that you don't perceive are going to persist, right? For languages that you don't perceive will persist. So the fact that people are taking on some of these larger research challenges related to Rust is also an indicator that it's going to be around and it's going to be in use. And so it's worth actually investing in some of that research.
And we will have to investigate Rust binaries, say, to make sure to see if there's any malware or surprises in them.
Yeah, surprises. We don't like surprises in code. We like surprises at birthday parties, but not in code.
And actually, if I could add on real fast,
sure.
David had just mentioned, part of the goal here of looking at Rust code is because in our reverse engineering work, we're looking at things like malware. We're trying to understand what the software is doing and how we can counter various things and improve our security. And as mentioned in the blog post, we've been seeing this uptick in malware that comes from these malware packages and all that are increasingly adopting other languages outside of the C family. And Rust is starting to be used a lot more, but there are some other languages too. And so as we see more malware taking advantage of vulnerabilities, and that code itself is written in Rust, and then maybe it'll take advantage of the Rust code, it's important for us to understand how the Rust ecosystem and other languages too, how all of the software plays together. And
I'm not sure that I'm happy that Rust is starting to be used by the malware community. I guess it is a sign of maturity, but it's also.
I think I would be more unhappy if it was being ignored by the malware community.
Okay. All
Say
right.
what you want about them, but they want their software to work just like you and I want ours to work.
Yep. If they're putting their faith in Rust, yes. I get you. So to finish off our discussion, for people that are out there, security analysts, programmers who are more interested than they were when we started on security vulnerabilities related to Rust, what kinds of resources are there besides your blog post in helping them understand where they need to look for those vulnerabilities and so on?
So that's a good question. For what it's worth, I've read a lot of information about Rust, about how to program in Rust. In our first blog post, Joe and I talked about some of the resources that you can use if you want to learn Rust. I have not read much in the way of Rust from a security standpoint, or rather, I read about how to write good Rust code, but I haven't read about how to keep yourself secure when running someone else's Rust code. That is some material that we still need more information on, and that's one of the reasons that we wrote this blog post. I specifically asked Garret to write what we know about source and binary analysis in Rust, because we haven't really seen a lot of material out there. I hope this blog post kind of starts the ball rolling and has people focus on this aspect of Rust.
Okay.
Because it needs more love.
There are some tools that we highlighted in the blog post, actually, that are kind of the beginnings of some static analysis of source code, Rust source code specifically. But these are all, research tools and, still being worked on academically. So they haven't been expanded enough to be able to go out to developers in more general use. So there are some tools to look at, but they need more development. And that's still primarily in the source code area. And like I said, in terms of binary analysis, in terms of the executable code analysis, there really is not a whole lot of tools out there, even in research, that have been designed and updated to work on Rust code. So this is definitely an avenue of future research that SCI and others can take. And we have our own tools that I mentioned at SCI, like Pharos and our Kaiju tool extension for Ghidra, which tackle a lot of these problems but haven't expanded into Rust yet. And so I think those are future things that we will look at.
This is a domain where we could use more maturity. And to be fair, C didn't get these kind of maturity either until really the 90s, when people started to take security seriously.
So I see more podcasts in our future, because I think this is an exciting. There's a lot of things to do here, and we're kind of we're in the upswing of the interest in Rust and how to make Rust more secure, how to use Rust in secure fashion. So I look forward to other conversations we're going to be able to have in the future about this. And I want to thank you both for taking the time to talk with us today and to give us that perspective on both Rust maturity and on some of the vulnerabilities that we need to be aware of when we're actually out there using Rust in the wild, as it were. So thank you both. And I need to tell our audience that to remind them that you can get this podcast wherever you want, wherever you get your podcast, if it's Stitcher, if it's Google, or my favorite, the SEI YouTube channel. It's available lots of different places. And so we encourage you to find it. And we will have references in our transcript to our prior podcast related to this topic, as well as lots of other resources that we've talked about here, Ghidra, Kaiju, etc. So please look at the transcript and find those resources and go forth and use them. And as David said, go forth and sin no more. So thank you all very much for joining us, and we look forward to future conversations.
Thanks for having us, Suzanne.
Thanks for joining us. This episode is available where you download podcasts, including SoundCloud, Stitcher, TuneIn Radio, Google Podcasts, and Apple Podcasts. It is also available on the SEI website at sei.cmu.edu/podcasts and the SEI's YouTube channel. This copyrighted work is made available through the Software Engineering Institute, a federally funded research and development center sponsored by the U.S. Department of Defense. For more information about the SEI and this work, please visit www.sei.cmu.edu. As always, if you have any questions, please don't hesitate to email us at info@sei.cmu.edu. Thank you.